The floor is yours, Dan.
All right, thank you very much. And I want to thank the organizers for, well, I know how much of an effort they put into organizing this, especially in these difficult conditions, doing it online and in person as well. Today, I will talk to you about a simple model of plane partitions, and more precisely of cylindric plane partitions. And actually, the goal of this talk today, I hope everybody can hear me, by the way. If not, please raise your hand in the chat or if there are issues. The goal of today's talk is to tell you or to try to convince you that complex probabilistic behavior can arise from considering simple combinatorial models, probabilistic combinatorial models that people have considered in algebraic combinatorics and in probability for at least half a century by now. And I'll start with a warm-up. And the warm-up is plane partitions. And more precisely, I'm going to look at trace and volume-weighted plane partition. So a plane partition is what you see in the figure. It's a stack of boxes in the corner of a room. It has a volume, the number of boxes, and it also has a trace. It has many other things, but so the trace is the number of cubes in the middle. So if you write the plane partition as a height function, this would be the trace, as in the trace of an actual matrix. The trace is just the number of cubes under the red tops. So it's equal to 12 here. And if you sum over all plane partitions, the partition function, what I call Z, has first been computed by Stanley, I believe, in the late 70s, and it's equal to the formula that you see below, to the nice product that you see below. If I put A equals 1, I just get to Q to the volume measure, the most natural measure you can think of. And for the purpose of this talk, I'll always be interested in extremal statistics. So I'll be looking at the height of this guy, at the distribution of this guy under this measure. I can look at other things. I can look at the distribution of this guy. I can look at the distribution of this guy. I can look at joint distributions. That's not important. I'll just focus on this guy. It turns out that using a theorem of Green and various combinatorial correspondence like the Robinson-Shanstad-Knuth and the Birch correspondence, the distribution of this guy, so what I call lambda 1, 1, the distribution of the peak, has many other interpretations. It's equal to both L1 and L2 in distribution. What are L1 and L2? Well, imagine that you have a field and each dot here is a random variable and they're equidistributed by diagonal. So this dot is a geometric random variable of parameter AQ. A geometric random variable is just defined here. It's the simplest object you can think of, probabilistically. These two are geometric random variables with parameter AQ squared. These four are independent geometric random variables with parameter AQ to the fourth, so on and so forth. So they're all integers. And now imagine trying to maximize over all paths like the yellow one, going from 1, 1 all the way to infinity. The maximum of that is what I call L1. Borel-Cantelli tells us it's almost surely finite. Now try to maximize over all paths going from here to here. This is what I call L2. So L2 goes in the perpendicular, L2 goes over paths that go in a perpendicular direction. And this is also equal to gamma 1 in distribution, where gamma 1 is the first part of a partition distributed as such. So this is a nice product, actually. This is a Schur function evaluated at, well, a principal specialization of a Schur function. And all of these are equal in distribution. And our first goal is to figure out what this is asymptotically when Q goes to 1. Otherwise, when the number of boxes here goes to infinity, when the volume goes to infinity. And it's simplest stated, well, the result is a bit, this slide is a bit dense, the result is a bit complicated. But okay, let's unpack it. So L, which is either one of those 4 random variables, in particular the peak of the plane partition, as Q goes to 1, e to the negative epsilon, epsilon goes to infinity. And in the critical regime, as the parameter of the trace, so remember I was keeping track of the trace here with the parameter A. As A goes to 1 as well, like this, it turns out that any one of those 4 things fluctuates as twice epsilon inverse log of epsilon inverse. Epsilon inverse is a big parameter. You can call it M if you want. And then it has fluctuations of the order epsilon inverse. So M log M, order of magnitude, and order M fluctuations, where M I just arbitrarily call 1 over epsilon. And the distribution is can be written somewhat explicitly and is a so-called Fredholm determinant. So it's a determinant of an operator. That operator is given here. It's this quantity in exponential variables times something. And this quantity, this operator, is called the Bessel operator, and it's actually a universal object in random matrix theory. So there's quite a bit on this slide still. So let me move on a little bit and to tell you why this distribution is nice and interesting. Well, it turns out that this distribution, G alpha, which is a Fredholm determinant of something a bit mysterious, at least in combinatorics, has 2 nice limits. When alpha goes to infinity, you get the so-called Tracy Widom GUV distribution, which has the property that it's actually universal in, for example, if you look at the largest eigenvalues of random Hermitian matrices with IID entries. If you look at alpha goes to 0, G of 0 is the Gumbel distribution, which also turns out to be universal if you look at the maximum extremal statistics of IID random variables. So in the second case, you looked at maxima of highly correlated systems, and in the first case, you look at maxima of extremal IID systems, maxima of IID systems, IID random variables. And this alpha somehow goes between the two. So you look at 2 different universality classes. One is the so-called, I suppose, Gaussian class, and you look at extremal statistics therein. And the other one is the so-called KPZ universality class. I will not talk too much about this. And this is where you see Tracy Widom. And this simple trace parameter that was first introduced by Stanley, I believe, in the study of plane partitions, kind of goes between the two. I should also say that Bessel itself, if you take the Fredholm determinant of this operator, that is also a universal object in random matrix theory, and it appears when you look at the lowest eigenvalue of random covariance matrices. So take X star, where X is a random matrix with some entries, some IID entries. X star is Hermitian, it's positive definite, its eigenvalues are positive, it has the lowest eigenvalue, which is close to 0. If that matrix is M by N, so this is going to be an M by M matrix, and M minus N is equal to alpha fixed, then you're going to see determinant of 1 minus this operator, as opposed to the same guy in exponential coordinates, universally as N goes to infinity. This is, for example, there are many results along these lines of Tao and Wu and Egdersh and Yao and many people in the random matrix community. All right, so if you take nothing from this talk, and I haven't mentioned our main result yet, if you take nothing else from this talk, what you should take is that very simple models, in our case, combinatorial models of plane partitions, if you look at natural distributions on them, they have this somehow somewhat mysterious but somewhat natural interpolation when you look at statistics, extremal statistics in our case, between two very different types of classes. One is maxima of IID, the other one is maxima of eigenvalues of random matrices. Okay, so I mentioned Fredholm determinants. What are Fredholm determinants? Well, if you have an operator that acts on functions by multiplication, this is you know, on a measure space, this could be a finite matrix, so then it's matrix multiplication. It could be an infinite discrete matrix, or if it could be an infinite continuous matrix, i.e. an operator. Its Fredholm determinant is just this. I think this is called the Sylvester expansion, perhaps. If you do this for a matrix, all of these are gonna be finite sums over all minors of the matrix, principal minors. And you can also write it like this. So that's a Fredholm determinant because this object is gonna be is gonna appear throughout this talk. This is just a reminder of what Fredholm determinants are. And now let me mention that we can actually go a bit further, and you'll see this when we're gonna talk about the main result, but let me mention it in one slide here. Depending on this trace parameter for plane partitions, so recall again that a to the trace here, so q, in order to see something interesting, you want to let q go to 1, because otherwise you have finite volume, you're not going to see anything interesting. But you have a freedom of playing with a. And actually, if a is 1, precisely 1, you have Gumbel fluctuations. This has been proven by Vershik and Yakubovich about 15 years ago. If a is less than 1, but fixed, so a doesn't go to 1, this has been, well, you have Tracy Widom fluctuations. So what you would expect from the main theorem, from this limit, on a different scale, and we proved this. And the result I showed is this transitional case when a goes to 1 critically. And I should say that that this interpolation was first discovered by Johansson in 2008. And actually, he was looking at a model of last passage percolation similar to this. So he was looking at maximizing paths similar to what I have here, with some differences. You have exponential random variables. You have a finite rectangle instead of an infinite field. There are some differences, of course, but this distribution itself and this interpolation was first discovered by Johansson in the study of polymers, of last passage percolation. All right, and now to the actual main content of this talk. So in this talk, we're going to look at, roughly speaking, the same objects, but now on a cylinder. What do I mean by that? So imagine a plane partition in a corner of a room, but now imagine that you wrap the room, well, it's explained here, you wrap it around and you identify the two vertical sides. So that gives you a cylinder, and this cylinder, for simplicity, has width 2n, twice n, capital N, and here is equal to 3. And so let me call lambda such an object, a cylindric plane partition. Alternatively, you can think of it as a dimer configuration of on a cylinder, because you have plane partitions are equivalent to lozenge tilings. Well, this is obvious in the picture, and lozenges are dimer configurations by simple bijections on the dimer configurations on the hexagonal lattice. And you can look at the cylindrical geometry. And let me tell you the distribution that people want to study in cylindrical geometry? Well, you'd want to study Q to the volume. But as you saw, it's interesting if you actually keep track of the trace as well, and perhaps of other things, but it's certainly interesting if you keep track of the trace. So we want to do the same thing as in the warm-up that I mentioned. Except that if you think about it for a second, this doesn't quite make the partition function finite. Because when you wrap things on the cylinder, you have this seam, and you kind of have to keep track of it. Otherwise, the partition function, even combinatorially, is not finite. So the seam is just the height, the total height of the things that you see here. The seam is equal to 3, so 2 plus 1. It's also the height of the things here because these are identified. And how do you keep track of the seam? Ideally, you could do it with well, in principle, you could do it with a different parameter, arbitrary parameter. But things are complicated enough with the number of parameters that we have now, which is a, q, and the width n, twice n. So let me simplify it a bit and just declare that the seam has this parameter to keep track of it. But again, we can do it with an arbitrary parameter. Things are just nicer if that parameter takes this particular value. So again, I have a trace. I have a 11, the number of things here in the middle, the number of cubes in the middle, a seam 3. And then this weight, if you sum over all plane partitions, has a partition function. So the generating series for such things is known. It's hard to attribute it properly because it goes back a while. So it's in McDonald's book as an exercise. The relevant sum over symmetric functions, Sagan and Stanley give a very nice bijective proof from the 80s. Kratenthaler computes this in the 90s, or maybe early 2000s. No, in the 90s using non-intersecting lattice paths. Borodin has recomputed this in the 2000s, and Jeremy Betea and I have recomputed this a few years ago using vertex operators. So there are many people have computed this quantity in more or less explicit ways. And I should say that such objects are actually interesting in theoretical physics and in algebraic combinatorics for independent reasons. And for example, if you look at Rojak's Ramanujan identities, there are some recent papers of Cortel and Jean Dus and where they where they use such objects to study various classes of Rogers, Ramanujan, and more general identities. And again, there they kind of look at the peak. Right, so let me give you some equalities in distribution. So again, I'm interested in the peak. I'm interested in the distribution of this guy. Let me give you some equality in distribution. First, lambda 1, 1 is equal to the first part, lambda 1 of a partition, which comes from this two-partition model. What's a two-partition model? Well, this is a Schur function. It's a skew-Schur function. These are partitions. In particular, it means, and I'm looking at a probability on two partitions, lambda and mu. It's a skew-Schur function evaluated in a principal specialization. I have this parameter A as well. The two partitions are correlated here. So there's some interaction between them that's fairly complicated. Mu also appears here. And then I'm looking at lambda 1. So I have this distribution. I trace over everything except lambda 1. Lambda 1, 1 is also equal to capital L plus kappa 1, where kappa 1, first of all, is independent of everything else. And it has this simple distribution. This is an infinite Q Pochhammer symbol. This is a discrete Gumbel distribution. And what's L? L is the longest polymer. So imagine you have a cylinder that looks like this, n is equal to 3 here. And you have these small squares on your cylinder. 1 in the first diagonal, 2 in the second diagonal, and from some point onwards, you only have 4 squares in each diagonal like this, in each horizontal line. And in these small squares, you put independent geometric random variables with parameters that vary according to the diagonal, to the square, to the horizontal line you're in. So here you have a geometric random variable with parameter AQ. And here, for example, every number in every square is a geometric random variable with parameter AQ to the 6th, because we're in the 6th diagonal. And you again look at the longest path the longest path using these two steps, these two sequences of steps, starting from here and going all the way to infinity. And lambda 1, 1 is equal to the length of that in distribution plus something independent. Incidentally, an interesting connection by Imamura, Muchikoni, and Sasamoto from 2021. Well, actually, they didn't prove this, so this is something extra you have to prove from their result. But this L has a nice interpretation. So this L equals in distribution rho 1, where rho 1 is the first part of a Q-Whittaker distributed partition. So there are these polynomials called the Q-Whittaker polynomials, the McDonald polynomials when t is equal to 0. Take them at a principal specialization, put the Q parameter to be Q to the N, capital N. And this L, which comes from a cylindric geometry, is equal to this rho 1.
Please try to wrap up now, Don.
Sorry about this. We started a bit late, it's true. Okay, so let me tell you the main result. And the main result is it has 2 parts. And the width of the cylinder is fixed and A grows critically, A goes to 1 critically. Then lambda 1 is the peak. They're the same in distribution. Grows as m log m with the order m fluctuations. And you get this Bessel kernel in exponential coordinates and in finite temperature. I should explain what that means in a second. When epsilon goes to 0. There's a second regime when n grows slowly, but A is fixed and grows like this. And then lambda 1 grows differently, order epsilon inverse with fluctuations epsilon to the -1/3. And you get a different distribution in the limit, which is this Tracy Widom distribution in finite temperature. So it's a Fredholm determinant of this kernel. And the Tracy Widom distribution in finite temperature is yet another distribution, somewhat universal, that interpolates between Gumbel and Tracy Widom as the temperature parameter goes to infinity or 0. And this Tracy Widom distribution appears in models of continuous fermions and matrix models. It appears in the KPZ equation, the Kardar Parisi Zhang equation, and there are many works on this. And our systems, first with Jeremy Betea, but of which I haven't talked about, and this one with Alessandra Ocelli, actually kind of makes a bridge between these two, between these models of random matrix models and between the KPZ equation, based on what I told you here. There are many other things you can do. As n goes to infinity, you recover, in part 1, you recover the Bessel kernel that I told you about before, which already interpolates between Gumbel and Tracy Widom. In part 2, you interpolate between Gumbel and Tracy Widom via this finite temperature thing. And all of these are there are many other limiting regimes, even interesting ones that one can do. And all of these things are discrete combinatorial models that correspond to systems that people have studied before in physics, continuous systems that people have studied in theoretical physics. Ledusal, Majumdar, and Sher come to mind, and collaborators. All right, I will skip the proof and I will thank you for your attention. Thank you very much. And apologies for the slight delay.
Okay, thank you very much, Don, for this talk. Do we have some questions from the audience here or from the viewers online? So if you're online, you could raise your hand or write in the chat. I guess I don't see if someone raises their hands, so maybe better if you write in the chat if you have a question. So I have a question then, Don. So you're talking about these cylindric plane partitions when you wrap the partition around and you need to keep track of this seam, but then this seam has a very special property that people think descends from it in both directions. So could you glue several plane partitions together instead and have several different seams?
So you can so what you're sort of saying, if I'm not mistaken, is that I only looked at things that go up here and then go down here. Like a profile where, well, where the plane partition increases and then decreases. But you can look at things that go up and down and then go up again and down, and then you wrap it at the very end. So you can certainly do that. Then you would have two peaks, and you can study that. We just chose the simplest model because this was already unknown. And but you can do what you suggested, if I understand your question correctly.
Okay, thank you.
And as long as the profile has, so as long as you glue two things that are going to be macroscopically separated, in the end, the end result is not going to change much.
Okay, I see. That's interesting. Okay,
so if you do things with different profiles, then you get into other. There's a whole zoo of things you can get into depending on the profile you use for here.
Okay, let's thank Don again for this talk.